Welcome back to the lab. We've got a plan, we've got some boards, and nothing can stop us now. It is time to test Seth, the 3D printer thermal runaway monitor. If you've been following this series, you'll know that we have a couple of concerns with this design. There are some potentially marginal startup conditions, but it all comes down to how large, how long, and how strong the glitches on the outputs of our comparators are. Perhaps there's some built-in anti-glitch functions in those comparators, and that'll leave our design in excellent shape. Perhaps not. Let's find out. Our tests fall into three categories: statistic-based tests, margin tests, and accuracy tests. What I'm trying to say is we really want to know three things about this design. How accurate is the temperature measurement? How much margin do we have in the startup conditions? Remember, we've built kind of a mess for ourselves. The 2.5 volt reference needs to be greater than the program bed and hot end threshold voltages, while OK field needs to be greater than 2.5 volts, while the program bed and hot end threshold voltages need to be greater than the thermocouple output voltage. All at the same time, the entire time the system is starting up. Basically, I just want to get a scope probe on all those nets, power on the design a bunch of times, and measure the margin. We'll do that with the system set to the extreme low and extreme high temperature ranges, and then we'll see what case is actually worse for margin. We made some strong assumptions in our analysis. Now is the time to validate them. Let's make sure the system behaves like we assumed it would. And if not, let's go back and recalculate things to make sure that this thing's really going to work. After that, we'll test the accuracy of the trip temperature by comparing what temperature our multimeter reads when the relays deactivate. So we'll be measuring the temperature as known by our multimeter against when our system responds. We'll check all four ranges for both thermocouples and see where that leads us. Those last tests, the ones based on statistics, well, one of them we can't really talk to today. It's going to be a long-running test, so we'll circle back in a couple weeks. The other one's pretty short. We're going to do 50 power cycles today, ensuring that the system starts up successfully all 50 times. I can get an Arduino set up, power cycling this thing repeatedly, but I'm not feeling that at the moment. We'll plug and unplug this device 50 times, manually, and count how many startup failures we observe. The second leg is trying to capture how many false positives, that is, failed prints, we observe over the course of time, capturing how many hours these devices last. Personally, I don't use my printers enough, but the end goal is to capture a metric that ends up measuring false trips per 1,000 hours or false trips per million hours. I want to really understand how often these fail, and when they do fail, how. So that's the goal. What happened in the lab during our live stream? First on the docket, a quick PCB assembly inspection. Remember, we had JLCPCB assemble these things for the cheap and really fast. The plated through holes look clean as always, a couple tears from the use of slightly worn out drills, but not so bad. After that, component placement looks very repeatable, no tombstones, good fillets all around, good times. The PCBAs came out clean, no random bits of solder on top of components triggered! But they were clean, which is amazing. And JLCPCB assembled these boards for about $2 a piece with the components. I'm floored. I'm blown away. I'm going to use this service again. Their online quote was accurate with no after-the-fact price hikes. The PCBAs got done on time and were delivered fast. My gripe is, as always with these Chinese assemblers, no ESD control. These things didn't come in an ESD bag, but that's a little less important for what JLCPCB is doing. If I'm only having them assemble resistors and capacitors on my board, which saves me a lot of time by the way, that can be tens or hundreds of resistors and capacitors, but if I have them do that, there aren't any ESD sensitive components on the board, so static control is less important. Basically, is JLCPCB's manufacturing service ready for full production runs? No. But I don't think that's what they're trying to do. Based on what they're offering, which is an SMT Assembly service for a limited selection of pre-selected components that I'm assuming they leave in their pick-and-place machines all the time, this seems like a service that's meant, from their perspective, to drive additional revenue for LCSC, a component distributor that's affiliated with JLCPCB, while for me, making SMT Assembly super affordable for the hobbyist so we can build complex designs with hundreds or thousands of components faster. Worth noting, they added a couple tooling holes in my board, so maybe add a comment on your assembly order about where they can place those, where you're all right with them modifying your design, or just add them to your board directly so they don't have to. They place the tooling holes in reasonable parts of my PCB, but if you have to have uber control over every aspect of the fab, this might bother you. Overall, throwing a few ICs on the PCBA to finish assembly takes a lot less time than the 300 resistors and capacitors that support it, and I am very glad that this service exists. This probably saved me 100 hours through the work they did assembling these 10 boards. By the way, I can tell I'm getting excited. I'm talking really fast. I paid for this with my own money. I'm not affiliated with JLCPCB in any way, and quite frankly, JLCPCB probably doesn't even know that EEforEveryone exists. I just had a genuinely positive experience with their SMT Assembly service, and JLCPCB has consistently done honest work for me at a fair price. I'm always a fan of that. Testing then. The actual design. What did we observe? Well, first of all, the startup margin looks great, and so does this scope capture. Thank you to you guys for motivating me to get the direct capture through the Ethernet working. This is awesome. So pretty much what we're observing is performance that aligns with our assumptions and less with the simulation, which destroys our main concerns about marginal startup. No matter what temperature range the monitor is set to, I measured 2.5 volts of minimum startup margin from 2.5 volts to OK Filt, which was my biggest concern. That's about as ideal as we're going to get. All of our margins came out as good as possible with an incredibly short glitch on startup that we could ride through no problem. That glitch is because the thermocouple monitors turn on faster than the thermocouple threshold voltage charges, like the RC network is slower than the IC, but I kind of like seeing the OK LED flash when it boots, and the voltage present at OK Filt shows that this glitch doesn't negatively impact the startup margin significantly. Sweet? Based on what we saw, I'd expect this design to start up very consistently. So we put our money where our mouth is. After 50 cycles, 25 from the AC to DC power brick and 25 from hot plugging the DC barrel jack onto the PCB, so one's harder, one's a faster transient than the other, we observed 50 successful power cycles with 50 attempts. Excellent. Check out the stream archive if you'd like the long version, but we've got some great explanations of what's going on and just generally hung out in the lab for a while. It was pretty great, so check out the archive. After startup, we investigated accuracy, which was pretty bizarre. We observed very reasonable error, 6 to 7% on both the extreme high and extreme low ranges for both, and nearly 20% error on the two inner ranges. Something doesn't add up here. One range being out of whack is relatively understandable, right? Maybe it's just an incorrect part or something populated incorrectly, but when both of those inner ranges have the same behavior for both implementations of the circuit, there might be something goofy about how we pinned out that switch. I think we might be putting two of our pull-up resistors in parallel somehow, where we told JLCPCB to populate an incorrect part. Something is messing with those two inner ranges. Funny enough, as we walked through the resistors populated to set our thresholds, the resistors that corresponded to the 7% accurate ranges were almost identically the ideal value, but the inner ranges that were all over the place, well, the resistor values were all over the place. So even if it doesn't make perfect sense and we don't have this figured out yet, they should all be 1% accurate resistance. Maybe this comes down to luck of the draw. Maybe I accidentally told them to populate a 5% or 10% accurate resistor. Where the heck would you even find one of those? But more investigations required. More importantly, the system's operational. When the temperature monitor trips, it trips and latches itself into the correct state. When thermocouples fail, Seth opens the relays. Our measured results fall within the expected performance based on our calculations and simulations. I am very happy with our testing today because we've proven that Seth works. I think that our testing today is a great testament to what happens when corners aren't cut. When analysis, simulation, and circuit theory are all applied to a design and the design is implemented well, correctly, it always feels great to turn around and have something work as intended. And I'm happy to report that that's the case today. Seth works as intended. There's only one more thing I'm going to do. Use it. I'm going to continue to use Seth to monitor my 3D printer and report back the number of failures per hour. So far, 100 hours of print time, 0 nuisance trips. We'll see if this continues to perform well as hundreds of hours turns into thousands and see what those failure modes turn out to be. Speaking of thousands of hours, if you have a favorite creator involved with 3D printing and would like us to reach out to them to get even more hours on this design, really test it out, we've got 10 of these things and we'll happily send one to whoever. So hey, you might even see a couple of these partially assembled boards turn up in our boxo junk on Etsy. You simply can never know what we're going to throw in that box. We've done a lot of projects. We've got a lot of spare boards. Could be anything. Could be a plant light. Could be literally garbage. Who knows? If you like this video and can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we'll wrap up this whole project with a summary video and then... guess we'll have to figure something out. probably more UPS stuff, but I think I'm going to take a little break here. I'm going to take a little breather, a creative break, if you will, reflect on how we've been doing and perhaps make a couple improvements. No worries though, we aren't going anywhere. There's still a lot to do and there's so much that we haven't discussed. I still have a lot to learn. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EEforEveryone, and thank you for staying till the end. Bye!